Hi everyone, welcome back to e-education, your go-to place for mastering electrical engineering concepts. In today's video, we will cover some advanced topics in AC circuit analysis, including sinusoidal steady-state analysis, resonance two-port networks, balanced three-phase circuits, star data transformation, complex power and power factor in AC circuits. Let's dive right in. First, let's talk about sinusoidal steady-state analysis. This is when we analyze circuits that are driven by sinusoidal sources after the initial transients have died out, leaving only the steady-state response. We can see the diagram AC source driving a simple RLC circuit. In this analysis, we use phasors to simplify calculations. A sinusoidal voltage or current can be represented as phasor, which is a complex number representing the amplitude and phase of the sinusoid. We can see the phasor representation of inductor. I is equals to Im cos omega t plus phi, Vs is equals to L di by dt equals to minus omega L Im sin omega t plus phi. For example, a voltage V of t is equals to Vm cos omega t plus phi can be represented as V is equals to Vm e to the power j phi. This makes the solving circuit equations much easier. Now let's look at the resonance in AC circuit. Resonance occurs in RLC circuit when the inductive reactance equals the capacitive reactance, causing the impedance to be purely resistive. We can see the diagram of series RLC circuit. In a series RLC circuit, the resonance frequency Fr is given by Fr is equals to 1 upon 2 pi under root LC. At resonance, the circuit's impedance is minimized and the current is maximized. In practical applications, resonance can be used in filters and oscillators, but it can also cause unwanted high currents in power system, so it must be managed carefully. We can see the graph. Now let's talk about two-port networks. These are the electrical networks with two pair of terminals used to analyze the behavior of complex circuits. We can see the block diagram of two-port network. Two-port networks are characterized by the parameters like Z parameters, impedance, Y parameters, admittance, H parameters, hybrid and ABCD parameters transmission. Each set of parameters provide a different perspective on the network's behavior. Let's start with Z parameters, also known as impedance parameters. Z parameters relate the input and output voltages and currents through impedance. We can see the equivalent network of a two-port network in terms of Z parameters. The Z parameters are defined by the following equations. V1 is equals to Z11 I1 plus Z12 I2. V2 is equals to Z21 I1 plus Z22 I2, where V1 and V2 are the input and output voltages, I1 and I2 are the input and output currents, Z11, Z12, Z21 and Z22 are the impedance parameters. These parameters are useful when dealing with the impedance networks and help in analyzing how the input affect the output in terms of voltage and current. Next, we talk about the Y parameters and or admittance parameters. They are the reciprocal of impedance parameters and are used to describe the networks in terms of admittance. We can see the equivalent network of a two-port network in terms of Y parameters. The Y parameters are defined by the following equations. I1 is equals to Y11 V1 plus Y12 V2. I2 is equals to Y21 V1 plus Y22 V2. V1 and V2 are the input and output voltages. I1 and I2 are the input and output currents. Y11, Y12, Y21 and Y22 are the admittance parameters. The Y parameters are particularly useful in analyzing networks where the elements are primarily admittances, like in AC analysis where capacitive and inductive elements dominate. Now let's explore H parameters or hybrid parameters. They are called the hybrid because mix both impedance and admittance parameters. The H parameters are defined by the following equations. We can see the diagram of equivalent network of a two-port network in terms of H parameters. The equations of H parameters are V1 is equals to H11 I1 plus H12 V2, I2 is equals to H21 I1 plus H22 V2, where V1 and V2 are the input and output voltages, I1 and I2 are the input and output currents, H11, H12, H21 and H22 are the hybrid parameters. The H parameters are widely used in transistor modeling and the other applications where it is convenient to use a mix of voltage and current. Finally, let's discuss ABCD parameters, also known as transmission parameters. These parameters are particularly useful in the analysis of cascaded networks. We can see the two-port network with ABCD parameters. The ABCD parameters are defined by the following equations. V1 is equals to A V2 plus B I2, I1 is equals to C V2 plus D I2, where V1 and V2 are the input and output voltages, I1 and I2 are the input and output currents. ABCD are the transmission parameters. Next, let's discuss balanced three-phase circuits. These are used extensively in power systems for the efficient power distribution. We can see the diagram of three-phase system. In a balanced three-phase system, the loads are equally distributed across all three phases, resulting in better efficiency and stability. The line and phase voltages are related by V line is equals to root 3 V phase, where V line is the voltage between any two lines and V phase is the voltage across any phase. Now we will talk about the star delta transformation. Star delta transformation is mathematical technique used to simplify the analysis of three-phase circuits. It involves converting a star configuration into an equivalent delta configuration and vice versa. We can see the delta and star configuration respectively in the diagram. The formulas for converting star to delta are RAB is equals to R1 R2 plus R2 R3 plus R3 R1 upon R1. RBC is equals to R1 R2 plus R2 R3 plus R3 R1 upon R2. RCA is equals to R1 R2 plus R2 R3 plus R3 R1 upon R3. The formulas for converting the delta to star are R1 is equals to RAB RCA upon RAB plus RBC plus RCA. R2 is equals to RAB into RBC upon RAB plus RBC into RCA. R3 is equals to RBC RCA upon RAB upon RBC plus RCA. This transformation helps simplify the calculation for complex three-phase systems, making analysis more straightforward. Now let's talk about the complex power in AC circuits. Complex power S is given by S is equals to P plus JQ, where P is the real power and Q is the reactive power. Real power P is the average power consumed by the resistive components and reactive power Q is the power alternately stored by and released by inductive and capacitive components. The magnitude of complex power is called the apparent power, denoted by mod of S. The power factor is the measure of how effectively electrical power is being used. It is defined as the cosine of phase angle between the voltage and the current. Also, the power factor PF is the ratio of real power to apparent power. Power factor is given by PF is equals to P. It ranges from 0 to 1, and 1 being ideal, meaning all the power is being effectively converted into useful work. To tie it all together, let's look at a practical example. Consider a series RLC circuit with given values of resistance, inductance and capacitance. We will calculate the resonant frequency, analyze the steady state response and determine the power factor. For our example, we will use the following practical values. Resistance R is equals to 10 ohm, inductance L is equals to 0.1 Henry, capacitance T is equals to 10 microfarad. Let's start by calculating the resonant frequency of this circuit. The resonant frequency is the frequency at which the inductive reactance equals the capacitive reactance, causing them to cancel each other out. The formula to find the resonant frequency Fr is equals to 1 upon 2 pi under root LC. Now we will plug in our values. L is equals to 0.1 Henry, C is equals to 100 microfarads or 100 into 10 to the power minus 6 farads. So putting these values in the formula, we get Fr is equals to 1 upon 2 pi under root 0.1 into 100 into 10 to the power minus 6. After 3 steps of calculation, we get Fr is equals to 159.15 Hertz. So the resonant frequency is approximately 159.15 Hertz. Next, let's analyze the steady state response of the circuit at resonance. At resonance, the impedance is purely resistive and is equal to the resistance R. So Z is equals to R. For our circuit, Z is equals to 10 ohms. If we apply an AC voltage source, V of t is equals to Vm sin omega t with a peak voltage Vm is equals to 100 volts and angular frequency omega is equals to 2 pi Fr. So omega is equals to 2 pi into 159.15, which is approximately equals to 1000 radian per second. The current I of t is in the circuit at resonance is given by the voltage divided by the impedance. I of t is equals to V of t upon Z is equals to Vm sin omega t upon R, which is equals to 100 sin 1000 t upon 10, which is equals to 10 sin 1000 t ampere. So the steady state current is 10 sin 1000 t amperes. Finally, let's determine the power factor. The power factor is a measure of how effectively the current is being converted into useful work. It is defined as the cosine of the phase angle between the voltage and the current at the resonance. The voltage and current are in phase, which means the phase angle is 0. The formula is power factor is equals to cos phi. Here phase angle phi is 0, so cos 0 is equals to 1. Therefore the power factor at resonance is 1, indicating that the circuit is purely resistive and all the power is being effectively used. To summarize, we calculated the resonant frequency to be approximately 159.15 Hz. The steady state response showed a current of 10 sin 1000 t amperes at resonance. The power factor at resonance is 1, indicating maximum frequency. I hope this practical example has helped you understand the concepts of resonant frequency, steady state response and the power factor in series RLC circuit. By applying these concepts, you can solve complex AC circuit problems efficiently. In summary, we have covered sinusoidal steady state analysis, resonance, two-port networks, balanced three-phase circuits, star-delta transformation, complex power and power factor. These topics are fundamental for understanding and designing AC circuits. Thank you for watching. If you found this video helpful, please give it a thumbs up and subscribe to the EE Education for more education content. Don't forget to hit the bell icon to get notified about our latest videos. If you have any questions, leave us a comment below. See you next time.